Okay, welcome everybody to our 157th Reading Online Sports Economics Seminar. It's a great pleasure to have with us Mario Lackner of the University of Linz again. He's presented a few times in the past, so he's a regular and knows how these things work. Before Mario starts, I will just do my usual roundup of various deadlines. If you submitted to the conferences here in Reading and in Duisburg, the Sports Economics, Sports Management, Reading Football Economics, and the Football and Finance conferences. We will be getting in touch with you shortly, but in all likelihood, if you submitted, your paper will be accepted, so you can start making plans, and we'll start to populate websites with information about travel and so on very shortly. There are no deadlines until this time next week. Next Friday, March the 15th, will be the deadline for the European Sports Economics Association Conference in Rotterdam, taking place in August. And also the workshop that Raphael Flepp, Romain Goyot and Carl Singleton are organising in Zurich, workshop on sports economics and natural experiments. That deadline is also next Friday as well. Followed by the following Friday, March 22nd, the Ibero-American Conference on Sports Economics has a submission deadline then. We are sponsored by the Sports Economics Review, should always mention that, and we're grateful for that sponsorship, which also enabled us to have a hybrid seminar last week with Rob down in Reading with me. This week, we're back to the usual format where Mario is in some other exotic location and I'm in my home office, but it's great, as always, to meet. And so Mario is presenting. There it is. When performance melts away, heat causes individuals to make more mental mistakes in high-stakes competitions. Mario, all yours.
Thanks, James, for the introduction. Always a great pleasure to be here. I thought back that this is almost exactly 1 year since I had my last presentation. And yeah, I am especially thankful since I was a late submitter, basically, and proposed to present this in early February. So by now you should see my slides. I hope everything is working out and you see also my cursor.
Yep, it's all good.
So what I'm presenting today is again, and always a pleasure as well, joint work with Hendrik Sonnabend, who is also in attendance. So whenever I miss a question or when I don't know what to answer, there is a safe backup in the room. So what I'm presenting today actually tackles the research question if heat stress or performing under heat conditions does actually affect performance, or to be more specific, mental performance. And we try to shed some additional light on what channels are actually driving potential effects there. And I think we can actually cover some holes in the literature that have not been addressed yet, partly due to the fact that the data was missing, and we think that we have a setting that might be ideal to actually look at what we try to answer with this empirical analysis here. So this project was actually inspired by a brilliant presentation held at the ESEA conference in Cork by Jan van Oers, who presented a paper on heat performance in tennis. And we kind of picked up from there and had some ideas about what we could do in this specific area of research. And we ended up what I want to present today now. So we want to investigate how productivity is affected by unfavorable conditions. And in a sense, we want to have a very specific form of productivity on our agenda, which would be cognitive or mental performance, however we want to call this. We are relying on the natural experiment to identify causal effects. And we look at games from the NFL, and we take the temperature that is recorded at the stadiums during the games as exogenous variation conditional on where these games are held and at what point of time these games are staged. And we have a huge amount of data basically covering all years from 2000 to 2022. So we think we can identify mental errors in our data. We think this is a setting that allows to investigate clearly what kind of mistakes are made and by whom these mistakes are actually made and what could be the channels driving how heat does actually affect the propensity to see such mistakes. The channels that we are going to focus at are body measures. So we are going to look at the body mass index. We will look at the possibility to coordinate and adapt to the conditions. And we will also look at how the incentives change during a game and how important performance actually is. Going to show you a series of robustness checks that tries to address some concerns that popped up along the way. And I hope that I can convince you that we find a robust evidence for a significant and quite sizable effect of heat on performance, mental performance, specifically under these competitive settings that we focus at. So why is this important? Yeah, don't need to say a lot about that. We know that global temperatures are rising. We know that we see phenomena like the one that is covered here on the right of these slides, where we have kind of periods of extreme heat in areas where extreme heat is not really expected or regularly observed, like this massive heat wave in North American northwest, basically, where temperatures occurred that have never been seen at these areas. And it was a phenomena that is likely to happen more often in the near future. So whenever something like this happens, we will see that the population is hit by a severe heat shock. And whenever a whole population is hit by these shocks, we do not only see massive health effects, but we would also expect that productivity is drastically affected, and most likely productivity in all sorts of different settings, while most studies out there focus particularly on productivity in certain areas like manufacturing or some very specific office jobs. So how should this work? So we can draw on what people from biology or health studies are telling us. So there's a thermal comfort zone for each human being, which is like between 18 and 22 degrees Celsius. It's kind of varying where you look at, so there's no consensus, but it's right in this area. And probably everyone has experienced how the best temperature zone has to look like. So whenever there is increased temperature, so if heat goes up, one way to mitigate this effect is to reduce physical activity. And in the end, we would also see that not only physical activity is affected and probably all sorts of productivities that are related to this, but also cognitive abilities are affected through how blood is redistributed throughout the body and so on and so on. So we would expect that increased heat would have an effect on the propensity of mental errors. And if you look at various settings like public offices, universities, all sorts of stuff, then for example, here in Austria, it's the case that for most of these buildings, it's prohibited to have air conditioning. And once we have such policies in place, which might make sense in terms of saving the cost of energy, in terms of saving CO2 emissions, in terms of avoiding further heating the outside within cities, then you also have to be aware of such a potential effect in order to avoid the negative effects, because all these guys sitting in the offices make their mistakes, and this has severe consequences. So this is actually taken from a 2022 paper by Park and co-authors who look at the performances of a very specific populations. This would be people doing school pupils basically doing high school exams over a series of years. And what they find basically is that the increase in outdoor temperature has a negative effect on performance. And this is really closely related what we want to do, but with some differences in the sense that we want to have a setting where probably performance is way more important than for these exams that are observed in this data. And we have a highly competitive setting with agents acting under these conditions that should actually be trained to work under these conditions and should expect them. So we could infer that what we might find could actually be a lower bound if we look at the whole population and all sorts of jobs that might be depending on some sort of cognitive performance. So the related literature to what we do is obviously tackling all sorts of effects that weather conditions could have on productivity. So there's a vast literature out there looking at all different sorts of weather phenomena that may affect productivity in all sorts of settings. And it's quite obvious that the results that are out there are all across the board, because typically what you find in treatments like weather conditions, you get all sorts of different results, always depending on what setting you look at. And there is a literature out there that focuses specifically on the effect of high temperature on productivity, and this productivity is mostly measured at manufacturing plants, for example, like this one paper here that is recently published, excellently published actually, that looks at the performance in manufacturing in India and has exogenous variation coming from different types of heat waves that are present over the observation time in different areas in India. And there is also other evidence coming from different settings, but mostly what these guys find is that productivity is actually negatively affected by temperature. But one problem, although they have this classical data, as we would say, is that in these settings, you have first got to rule out that it is not something like changes in the electricity prices that might be due to severe weather phenomena. You have to rule out that there are no changes in the preferences of these agents that are observed. So you could, for example, tend to want to more time outside if the weather is fine, and this might reduce your effort in at your workplace. And we think that we can rule out this potential biased effects because we have a setting where prices stay constant when weather changes, and we do see that these agents basically during these competitions have no other life to speak of, and they should be really focused irrespective of what weather they observe. So there's also some research out there that looks at how individuals work under heat stress, coming from the early medical literature telling us that they work less accurately when experiencing heat stress. We also have some results on mental performance, mostly coming from various types of exams, like the one I showed you before. And there's also evidence out there that heat actually does affect decision making. So this is evidence coming from judges in the US. When the heat outside goes up, basically what is observed is that the court decisions are actually affected, although they are done indoors, which is a surprising finding considering the fact that you should not be affected once you enter a building that is air conditioned and where you are actually in your comfort zone working here at these court cases. And there is also literature out there showing that workplace injuries are affected by working under heat conditions. And there is a growing literature using sports data, basically showing that people's judgment changes, looking at MLB data, basically showing that heat does affect how balls and strikes are called in Major League Baseball. There are two papers out there on tennis that try to show how performance and adaptation do play a role when heat is affecting these players. And there is also a paper out there looking at archery. And also there's evidence on increased rate of mistakes when heat is out there. So this is a growing literature looking at sports. We try to augment what all these papers basically show us by trying to understand what are the channels behind these effects. And we try to specifically look at physical characteristics of people, and we try to understand how the dynamics within these competitions are driving these effects. So our institutional setting is the American Football League, NFL. So this are the basic rules that you have in American football. I don't think there is too much of a need to tell you. In essence, we have two teams competing in games that are divided in 4 quarters with an intermission of 12 minutes. Each quarter is 15 minutes long, and we have always one team in the possession of the ball who has a sequential chance basically to advance the ball towards an end zone, and you can score by several different ways. And there is also a team defending this end zone, and in the end, it's a game that is highly sequential, and this will help us in our data and will help us how we identify basically our effect or the channels that might be driving the effect that we want to investigate. So the NFL is one of the most prolific leagues worldwide. So the annual revenues are quite substantial. The salaries range all over the board. I mean, there are minimum salaries that are quite low actually compared to other leagues, but the salaries can go up substantially. And we have 32 teams. This is very important for our setting that compete in 16 regular season games. This has just recently changed. We have increased to 17 games, and you will play some of these games at home in your home stadium, and you will play some of these games away. So whenever there is a question, and I was too quick on some specifics here, don't hesitate to jump in. That's fine for me. So teams are located basically all over the US. So if we look at the stadium locations here, then we see that we have many teams here in the east of the country. We have lots of teams here down in the southeast. These will help us identify our effect. We have some teams here in the west, southwest basically, and we have also one team located up here. So these are locations here for the 2022 seasons. This is the last season that we are considering in our data. So we have still a majority of open air stadiums. I think this will probably change in the next decades because domes and fully indoor stadiums are becoming more and more popular in the league, basically to have a chance to stage a Super Bowl, which is not done usually in cold weather conditions. So if you do not have a dome, you have 0 chances basically, or very small chances to have the Super Bowl, which would be the final of the league, defining who is the champion. And we have also stadiums where we have either a dome with a fully closed roof, or we have a roof that is retractable. And in our data, we can observe whether the roof is actually open or closed. In indoor stadiums, or when the roof is closed, we typically would expect the temperature ranging between 70 and 75 degrees Fahrenheit, which is rather in the upper bound or close to the upper bound of the human comfort zone. This could be actually connected to increasing concession sales, but might also be due to the fact that these venues are actually air conditioned, but when you get it full with people, then it might heat up anyway. So whether we categorize them as having 70 degrees Fahrenheit or 75 doesn't really change our results at all. So an important fact is that the NFL never cancels any games due to bad weather conditions, except if there are thunderstorms or if it's actually not possible to stage a game due to snowstorms, or if there is a severe snow coverage there. But we would not see any games canceled because it's too cold or because it's too hot. So I do not know any examples where something like this really happened, because I've seen games where it was freezing cold and I've seen games where it was really, really hot. We had some games that were postponed, but that was mostly because some storm was approaching and it was not safe to play. But it was not really due to extreme heat, which would obviously be dangerous for our identification here. So we take data basically for all these games that we look at here in this period from 2000 to 2022. We omit the 21 season because it was the one season that was severely affected by COVID. And in the end, we end up with over 6,000 games, and we have slightly above 1 million observations in terms of play-by-play data. So we know exactly what is going on at this specific down or this specific event during a game. And our outcome of interest will be penalties that are associated with mental errors. So we augment this play-by-play data by NFL roster data. So we know which characteristics these players have that are either on the team during a specific season and are most likely also competing during an observed game. And we know specifically for a large share of all penalties which players actually committed them, which players were guilty. So we also have data on match characteristics. So we know what weather conditions were noted by NFL officials during, or basically at the start of the game. We also augment this by additional weather data that was collected for weather stations closest to the focused NFL arena. So from there, we also have weather data for domes or indoor stadiums. So we can also proxy what the weather was outside for these stadiums, which opens up a nice placebo treatment in the end. We also use some historical weather data. This is not so much a focus of this presentation here, but it also helps us to show how teams actually adapt under these conditions. So looking at our research design, we want to find an indicator for mental errors. That's why we focus on penalties that are observed in this play-by-play data. The penalties clearly state what was the reason for this penalty, which player was guilty, if there was actually a guilty player, which is not always the case. And in the end, we observe almost exactly 77,000 penalties, which is almost 8% of all observations are recording any type of penalty. When there are two penalties during a play, which is certainly possible, then we take the one that was enforced and that was also in effect because it was penalizing one or both teams. So starting from this, we wanted to find a list of penalties that is associated with mental mistakes, where one of these players or possibly even the coach makes a mental mistake by not staying focused, not staying within the game, not staying disciplined, whatever you want to call it. And in the end, we end up with slightly above 18,000 penalties that are associated with this. We carefully did this based on the definitions of these penalties in the data. And we tried to find mostly penalties that are independent to crowd noise, because that would be a dangerous thing to our identification strategy, because that would mean that more or less people could go to a stadium due to the weather conditions. And if this is actually affecting the prevalence of any type of penalty, we would see that our estimates would ultimately be biased. So the list of all penalties that stay in the category that we will focus on is presented here. So we have numerous categories in there. It's actually 22 at this point of time. And we have some in there that could be the mistake of any of the coaches on either team, but most of them are to a certain degree, obviously, due to a player not staying focused, not staying disciplined, and making a mental error. We also try to avoid any sort of penalties that could reflect some strategic element. For example, you could have a pass interference penalty, which is a very common type of penalty, but you want to do this, for example, if you want to stop or prevent the opposing team from scoring. And this would be a strategic element and not really a mental mistake. You could have made a mental mistake before, but on the other hand, it could be actually quite smart to have a pass interference call instead of giving away a touchdown or any other type of score subsequently. Some of these penalties that we have in there are actually penalties that are associated with some violent behavior or some form of violence. And we will also exploit this later on and show some evidence whether it's actually violent behavior or really mental mistakes driving what we find. So this is basically our outcome variable, and our treatment are the temperatures that we observe during these games. So we look at the weather conditions that are conditionally random based on where and at what weekend basically a game takes place. So we observe NFL games that are played under extreme heat, exceeding 100 degrees Fahrenheit. So that is really extremely hot and going up to 40 degrees Celsius. So we have basically a variable defining heat games as all games being above 85 degrees Fahrenheit. So this is not an arbitrary choice, but it is taken from the literature. It's actually the JPE paper by Ramanasan and co-authors who look at manufacturing in India, and they find that their effect basically starts at 85 degrees Fahrenheit. So this was a point where we started, and we kind of stuck to it because it's quite intuitive and it's fitting to the personal experience that you probably do not want to have a hard workout or any form of heavy physical activity when it's 30 degrees Celsius outside. We have a placebo treatment focusing on air-conditioned indoor matches, which I will present to you in a minute. And we have no spillovers and negative externalities, meaning that the input prices are staying constant. We have no power outages like in manufacturing in India, where when the heat goes up, you can produce less electricity, and this might change the conditions that you are working under. We have no spillovers from other industries. We have players that should not change their preferences because they would like to spend more time with the families due to the good weather, because in the end, during the season, they are very committed to doing this very specific type of job, and they have few outside options anyway. So we exclude the 2020-21 season due to the fact that this was COVID restricted. We don't want to have these in our estimation sample in the end, because we have no or very drastically reduced crowds present, and this might also affect what we find. So we wanted to shy away from these games. So this is our experiment, basically in one graph. In the end, we see here the probability of a heat game over the course of the season. So these are 18 weeks because we play 17 games, and each team basically has a week off where it has no game scheduled. And we see that the average temperature decreases towards the end of the season, which is natural because the season starts in September and the regular season typically finishes in very, very early January. And we see that the probability to observe any penalty stays remarkably constant, and it decreases slightly towards the end, probably due to the fact that some of these games are of lesser importance and some of these games are of higher importance. Both phenomena might have a decreasing effect on these probabilities to observe a penalty. What's important here is that from week 10 onwards, the probability to observe a heat game is really, really low. So it's probably connected to some stadium locations, most likely in Florida, I would say, where it's still possible, but the probability is so low that our preferred sample is actually ending in week 10. So the temperature distribution looks like this. We have a spike here, which is due to the fact that we have these indoor stadiums where the environment is fully controlled and air conditioned. And we see that it is going up to an area well beyond 100 degrees Fahrenheit, but we also see it's going down to freezing temperatures as well. So just a quick look at the descriptive statistics. We see heat games and no heat games. In the end, we have 173 heat games. We have slightly over 25,000 plays from these games, and the vast majority of games are non-heat games. And if we look at these key variables here, then we don't see much of a difference that would be too concerning in terms of what we do in our estimation strategy. How does it look like? Basically, we want to explain whether a penalty was observed during any of these almost 800,000 plays that we end up with in our final sample. And we want to explain this with our binary variable, whether we have temperatures on game day or when the game actually starts above 85 degrees Fahrenheit. We have a huge vector of control variables in there, and we have home team season fixed effects. We have week fixed effects, and we have away team fixed effects. So the list of controls kind of includes everything we can control for. What's kind of important, or where I want to point to, is we have the average body mass index of the away team in order to proxy how susceptible they should be to heat in the end when they compete. We control for other weather conditions, we control for attendance, and we use dummies for the referee crew, the down, the quarter, and all sorts of stuff that's in there, like the weekday, the position of the ball, the intermediate score, everything you could think of that might affect how high the probability is to observe a penalty. So the standard errors are clustered on the game level. This is the level where our experiment takes place. So game stays, the temperature stays more or less constant over the game, and we only have one value. So this is the experiment we need to account for, and we cluster the standard errors on the game level. So these are the first results, and it's divided here in 4 columns. The first model we estimate actually has a linear effect of temperature in degrees Fahrenheit on the binary outcome variable, whether one of these penalties is observed with a mental error or not. And we see it's a very, very precisely estimated 0. So we don't see any linear effects, which kind of rules out that we have an increasing probability of a penalty along the distribution of temperature. And this also is the first argument against that we see an effect, positive or negative, when temperatures are very, very cold. And we also have some evidence that it's not really the cold temperatures driving what we find. Going to a specifications where we have dummies for all these parts of the temperature distributions, we see that we do not see any effects for all these intervals that are here below 70 degrees Fahrenheit. We have the reference category, which are temperatures from 70 to 75, which is not only close to a comfort zone, but which is also the temperature that is observed indoors. So these are the stadiums that are most likely not affected by heat at all. And if we look at the high temperatures, we see that we have a positive and significant effect once we pass the threshold of 85 degrees, and it stays up there if we see games at 90 or larger. So if we take our binary indicator, we basically cover these two here and compare them with all other games, and we see that the effect is 0.45 percentage points increase in the probability of a penalty, which is a sizable effect. And I will show you that in a minute when I go to the different samples. If we reduce the sample to weeks 1 through 10, we get a very, very similar result, and it's still statistically significant at the 1% level. So let's do some robustness check. If we use alternative fixed effects where we use stadium dummies rather than home team season fixed effects, we get about the same estimate. This is our baseline estimate, and if we estimate a semi-elasticity, then we see that the propensity of a penalty increases by about 25%. So that's quite a sizable and large effect that we estimate here. If we add additional controls, like for example humidity or wind speed, then we lose some games, but doesn't really change anything. And if we have all penalties as the dependent variable, then we get an estimate that is even larger, but it's getting less precise, which indicates that we are getting lots of noise in there, which we in the end do not want anyway. But this would be too broad a category to really nail down the argument that mental errors are affected. If we look at games where we exclude all cold games, still the same effect. So not the cold games are driving our result. If we ignore all the plays that are observed directly after a penalty, we do not see any different effect, or the effect does break away, which means that it is not the increased volume of plays doing the trick here. And if we look at the full season, basically covering all weeks, we get pretty much the exact same result as the baseline result, so no change here. So whatever we look at here, our effect is pretty robust, and whatever we do, it doesn't disappear. If we look at the placebo treatment, basically coding all indoor stadiums as if they were outdoors and measuring temperature by the closest weather station and indicating the same category as here, having a variable that is 1 if the temperatures outside are above 85, we do not see any effect for these indoor stadiums. So this is actually contradictory with the finding that these judges also change their behavior once they are indoors. But here it's really a different setting, because it might be a conscious decision by the judges to make decisions due how the weather is outside, because they could this finding could reflect a change in preference. For example, it could be quicker for them if they have a negative decision, and they might be home earlier if they make this decision quicker, and this might reflect a change in preferences rather than really this effect of heat on this decision making. So further robustness here. So something that might play a role is how you are exposed to sun. So we observe in our data when the kickoff of this specific game was observed. So we, from that, can construct a measure where we can distinguish whether a game was likely to be played under direct sun or not. And if we split our sample between games where sun was for sure present, at least for the majority of the game, and where no sun was present for most parts of the game, either due to the fact that the game was late or that the weather conditions said that it was cloudy during some parts of the game, we see that the effect is present for both, but sun might play a role in actually pushing this a little bit up. And if we have a placebo treatment where we do not code it as a heat game, if the temperature is actually high, but when we code it as a heat game, when it has full sun exposure and the kickoff was really early, then we do not see any effect. So sun might not really be what's explaining this, although it might push the effect a little bit upward. If we look at humidity, then you certainly know that under humid conditions, heat is more severely felt by human beings. We see that if we look at only low humidity games, basically meaning that we look at the below median humidity in our sample, then we see that we are very close to the baseline effect. So from this, we conclude that humidity is not what is explaining our results. And more on this is coming in a few slides. So in the end, you might still believe that it is probably one of these penalty categories that's doing the trick, or you might say, well, it's not really the players, but those old coaches that suffer from heat. So it could be that a very specific type of penalty is actually driving what we find here. For example, 12 men on the field might be a mental mistake actually made by the coach because he does not give the right assignments or the right formations to his players. And in the end, we should see that if we take a jackknife approach and serially omitting one of these penalty categories from our sample. But what we find is, irrespective of which category we omit from the sample, we always get the same estimate and are very close to the baseline. A further robustness check is presented here by looking directly at the heat index. This has been done before, for example, in the archery paper, where they don't look at heat directly, but on the heat index. And the heat index is basically converting temperature and humidity, relative humidity, into an index that should describe how players actually perceive the temperature. And this is an important thing because most of our treatments actually come from locations like Florida, North Carolina, or Washington, D.C., where humidity obviously plays a role. And if we play around a little bit with the threshold here, where we have the blue estimates basically changing how we define our explanatory variable, starting at 80 degrees Fahrenheit and ending up at 89 degrees Fahrenheit, because then our sample gets very, very thin. We see that the effect is increasing, and we see the first significant effect at the 5% level here at 85 degrees, but then it stays up there. But it's also already positive earlier. It's just not statistically significant at the 5% level, but on the 10% level. And if we look at the heat index, this kind of pushes up what we find here, in a sense that we have a zero result going up to a felt temperature of larger than 91 on the heat index. And then we see comparable estimates up to a heat index of 95. So they are quite the same statistically as the estimates from the standard temperature measure. So we conclude from this that it is not humidity doing the trick here, but it is really the temperature and not the humidity explaining our effect. So is it actually an effect of heat on emotions or aggressive behavior? So there's a literature out there that documents that heat waves as a treatment affect how crime rates behave and how violent behavior develops. So we think that we can look at our penalties in the sense that we only take those where there is an association basically with aggressive behavior, like taunting or roughing the passer, whatever. And you could also see some penalties where aggression does not play any role, like some procedural mistakes, like a substitution mistake, 12 men on the field, whatsoever. And if we take these two categories and we have this nonlinear specification here, we see no effect. If we are below the reference category, where we have the domes in there, and then we see no effect up until 85 degrees Fahrenheit, and then both categories increase as estimated before, with less precision here in the 90-degree Fahrenheit and upwards category, which is due to the fact that we split our sample, the outcomes basically, meaning that we have less precision in the estimate, but we rule out that this is an effect of heat on emotions or violence. So another point one could make is that it is actually the referees making the mistakes. So I mentioned the one paper that is looking at umpires in the MLB in my literature slide. And what they find is that the judgment got worse if these referees actually moved from colder locations of a game to hot locations, and they experience a drastic temperature change, and this affected their judgment. So what we did is we collected all challenges, irrespective of the fact whether it was initiated by one of the teams or by the officials. So any automatic challenges in there as well. And our dependent variable here is whether the penalty was upheld, then it was 1, or 0 if it was reversed. And if we take the same approach as before, we don't find any effects that are significant on the probability that these penalties are either more or less likely to be correct or correctly done on the field. And it's kind of quite unrealistic to assume that also the video referees are affected, because they are for sure going to be in an air-conditioned and fully controlled environment. So it's most likely not the referees making the mistakes here. So let's look a bit on the channels. If we look at what others have done, for example, the room to coordinate or to adapt, then we can look at, first of all, how this is affecting offenses and defenses. They are kind of equal in the effect. The effect is much smaller because we see here only half of the sample basically from all the penalties. If we look at plays that either after a break, could be a timeout, it could be an intermission, it could be a TV timeout, it could be an injury, whatever you have, then we see no effect here. If we look at plays that were directly observed after another play, with the only time between being what is on the play clock, or how long you have time basically to initiate the next play, then we see this large and significant effect here. So whatever we find is actually mitigated by working probably slower and having room to coordinate. So this points into the direction that whenever we deal with extreme heat and want to avoid mistakes, slowing down probably might help. If we look at more evidence here on how sudden changes of how you experience this heat does affect what we find, then we can look at whether you moved from one game to the other and you experience a change in the temperature during the game equal or smaller than 10 degrees Fahrenheit and larger than 10 degrees. Then we see that these games where the team, or both teams basically here, experience such a change or such an increase from 1 week to the other by more than 10 degrees Fahrenheit, then we estimate our large effect. For home teams, we don't see much of an effect at all, but for the visiting team, this effect is very, very large. And you could imagine that this might be the case because you are actually going to an unfamiliar territory. So once you prepare for a season, you might experience the conditions you're going to play on later anyway, because you prepared mostly during June, July, and August for the season, and you will compete in September, October, November, December when it's cooler. So you might be prepared what you are expecting during these games in later stages once you train under hot conditions before. More on the suddenness is presented here when we look at time variation within games. If we split up the quarters and combine basically quarter 4 and overtime, we see that right at the beginning of the game in the first quarter, we see this strong effect. This effect completely disappears in the second quarter when they have accustomed basically to the conditions. Then we see the intermission where players go to fully air-conditioned facilities and have all the amenities that you can wish for as a professional athlete. And then once they go back on the field, the effect is basically where it was at the beginning of the game and somewhat disappears towards the end of the game. But it's still kind of there because another effect might kick in that I will show you in a couple of slides. So one important focus here of our analysis is physical characteristics. So we wanted to look at how the body mass index of the players that are found guilty of a penalty is actually driving what we find. And we divided the sample in 4 quartiles of the body mass index, and our outcome variable is only one if you are if we observe a penalty by a player falling in one of these categories. And we see that there is no effect in the lower 2 quartiles, and then the effect increases to very large semi-elasticities actually, and it stays up there for the quartiles 3 and 4. So now you might say, well, it's the body mass index doing the trick here. And we actually argue if we look at professional American football, then we would have a body mass index that is actually quite similar to the body mass index of a general population as compared to the body mass index, for example, for professional tennis players who are all well-trained athletes with very low relative shares of body fat in their bodies. But we think that the BMI in the professional football team is much, much closer to what we would expect in the general population. If you still say that they have much more muscle and their body mass indexes are going up because of this, we can offer some alternative approaches here. First of all, we took an approach developed by Trefason in 2013, which is an alternative body mass index that has a different exponents in the height component and a different parameter here for the weight component of the body mass index. And this actually changes how you would see the body fat muscle trade-off. And here's a direct quote from this publication saying that if you converted 10% of body volume from fat to muscle, which is probably impossible for someone who is not a professional athlete, then your body mass index would only increase by 1.8%, which is probably negligible and would not make any difference. If we take this alternative body mass index here, we get pretty much the same result. Actually, we find that the increase is more as we would expect it, in the sense that we have a very clear zero effect here in the lowest quartile, and then it slightly increases to these significant effects here in the upper two quartiles. Another approach, if you still don't believe that the body mass index and how overweight or obese these players actually are does do the trick here, we can look at another approach, splitting the sample now for all players weighing more than 260 pounds. So these players are actually quite heavy. And by weight category, so we split it up in 260, 280, and so on. We have these 20-pound categories. We take only players that were penalized that are heavier than this. And by weight category, we look at the medium height of these players. And we run two regressions for those players that are above the median height and those players that are below the medium height. And if you weight like more than 220 pounds and you are below the median height of this weight category, then it's quite kind of hard to make the argument that it's only body mass coming from additional muscles, but it's most likely that really some form of obesity is actually observed for these players. And we see that only for those that are relatively smaller in terms of their height, we see the effect that we had before. There is a zero effect for those players that are relatively taller within these categories. So from this, we conclude that it is really most relevant for human beings that are in areas of the body mass index that would indicate obesity. And this would conclude that heat would actually affect a general population probably more than we would observe in a population of professional athletes. If we look at the importance within the game to perform, then we can look at low probabilities to win the game observed at the current play, medium probabilities and high probabilities. Looking at all pooled penalties, we see that the effect is largest actually when you have a very low probability to win the game. And this carries over to penalties committed by the team in possession of the ball, as well as to the team that is defending. We were first surprised to see these results, basically, because we would have expected that if you see like a medium probability to win the game, then the importance to perform might be the highest, and we would see effects there. But what's actually doing the trick here, and what our descriptive analysis is pointing to, is that the plays that are observed in the first category here always are those plays that are observed when both teams play under a high pace, which is kind of obvious, because if you are down and your probability to win the game is very low, with a game that is bounded basically upwards in terms of how long it can last, you have to play fast in order to close the scoring gap and have a chance to win. So speed kills here and causes the effect that we observe. So let's sum up. In the end, we exploit this natural experiment and we try to identify the effect of heat exposure on mental performances, or specifically the propensity to make mental mistakes. And players are roughly 25% more likely to be sanctioned for an infraction associated with a mental error if the game day temperature is 85 Fahrenheit or larger. We see a strong effect for above median BMIs. So we think that your physical characteristics are responsible for how you can actually cope with heat. And we find that we observe the effect when there is little room for coordination, when there is little room to adapt to the conditions, or to coordinate and slow down, and basically avoid these mistakes by probably getting refocused and slowing down your work pace. We find no heat effect for air-conditioned environments. So outside heat is not carrying over in our setting, which is not not just a nice placebo test, but is also contributing to the literature, as other findings suggest that it might actually be carrying over. So we look at a population of highly trained, constantly monitored agents basically in our competitions. And if we really consider the fact that probably those in responsibility of building these teams should be aware of something like this effect, that what we estimate could be a lower bound for what we could expect for a general population. And once we consider the effect that 25% increase in the mistake rate, then this could have a large effect on the productivity in a setting where the general population is involved, as discussed before. So that basically wraps up what I find here. I'm going to leave you with one of these players and a fascinating quote that I found, actually from the franchise now currently in Las Vegas, where heat is obviously daily business, and it kind of resonates quite well with what we find. And thank you very much so far, and I'm really looking forward to your comments and questions.
Thank you very much, Mario. Perfectly timed. I'm going to give you a team's applause. And we've got plenty of time for questions and comments. Ian, first up.
Hi, Mario. It's Ian.
Hi.
So thank you for the presentation. It's really interesting. Just one thing that was a bit puzzling to me at the start, when you showed the two samples, it seemed like the number of penalties was the same in the hot and the cold group, and then it was only when you introduced all the controls that you get the effect. Is that right?
What result do you
So just
mean?
in the descriptive statistics right at the start, there didn't seem to be a difference between this one.
You mean here?
So
yeah.
Is there a difference here between the heat gains in terms of penalties and the not heat gains? Doesn't seem to be. But then when you run the model with all the controls, you get an effect. So I was wondering, what are the relevant controls that's going to be giving you the effect when you control for everything, and it's not enough to override what's going on in the overall descriptives.
That's I mean, you don't see it in the overall mean, because not all penalties are alike, basically. So I mean, these games are heavily selected, and basically you cannot compare them by just saying, due to the relatively low number of having like 170 heat games, the number is so low that we can have games that are more or less competitive, for example, and then you would see that the overall propensity of penalties might actually be the same. But in the end, if we observe them on a play-by-play level, then you might see the difference in the end. But here in the overall mean, you don't see it. And I would not be able to tell you what level of controls is doing the trick, because I don't have the slide with the gradual model build. But it's not really pointing to one of the covariates doing the trick. I think most important of them would be that you control for the location, the type of stadium, obviously. And the other thing would be that you kind of control for how these teams actually look like, and what's the intermediate score and stuff like that. So yeah, but that's a good point to look at.
And then the other thing that was which I found a little bit interesting was, so you didn't find an effect with the referees, and the referees are the ones who, for every decision they make, is a mental decision. So if this was really a story about heat affecting mental decisions, I would have thought we would have seen it in the referees as well. And that doesn't seem to be the case. That was a little bit of a surprise, perhaps. But then I wonder if your BMI story explains away that. So maybe the referees are all skinny, and if you're only getting these effects for the the big guys. It's this combination of being big and hot that leads to your mistakes.
Yeah.
Is that fair?
I think that might be one part of the explanation, because I don't think, I mean, you have, I wouldn't know of the official guidelines or the official requirements to be a referee at the NFL, but if you look at these guys, especially now, when
they're not 300
the
pounds.
Yeah, I mean the older generation probably has left the league, and it's quite remarkable how well in shape they are. But I would assume that is kind of explaining some of it, and the other thing might be that in the end, what they make in terms of their decision could be reflected by having made a decision basically that is. Like, you don't have one guy making the decision like the umpire in the MLB, but you have guys getting together, discussing whether the penalty should be enforced or not. So I think that this might mitigate some of the effect. But yeah, we don't find anything for this. Maybe there is other ways to tackle these mistakes by the referees, but it is at least not with the penalties that are or the plays that are reviewed in general. Yeah.
And then just one last quick one. So on the BMI ones, I was wondering if you controlled for playing position, because the heavy guys are all, in the guard position, and they're probably the ones prone to going offside, whereas it's the lighter players who are at the back, the cornerbacks.
Exactly.
They're less likely to make mistakes.
One of the problems is that we cannot control for the position, because we have so many plays in our sample where no penalty is observed. So we don't have any position there. So we can only mess with our outcome variable basically and define it by what kind of category we're looking at. So we could look at different positions separately, that we could do.
Okay.
Whether it's like the front seven being affected, whether it's defensive backfield.
Because when you drew up your list of penalties, I thought where most of these are being committed by either the offensive or defensive line, and those are the heavy guys. Those are the 300-pounders.
Exactly. Yeah.
All right. Thanks very much. It was really interesting.
Thanks. Excellent comments.
Great. Thanks, Ian. And then Georgi has his hand up next.
Hi, Mario. Thank you very much. Terrific job, especially the robustness checks. I just have a few questions in terms of, do you have any means to control the running score of the game? And the reason I'm asking is there are some, like, not all penalties are equal. I think so. For instance, there can be penalties that are purely drawn due to frustration. Like there's a defender who's coming in and just grabs a running back's face mask because they're already down like 30 points. Some penalties like taunting might be attributed to closer games where, a wide receiver receives the ball, runs like 60 yards after catch, does like, a little peace sign and draws a taunting penalty for that. Like it happened with Tyreek Hill a couple years back. So, and then, for instance, in some closer games that, for instance, the team is leading by a bit, the coach is deliberately asking the punter to melt as much of the clock as possible and in turn take the delay of game penalty, which is only 5 yards. So do you have any account for sort of differentiating the penalties across different scores and game narratives?
Yes. Excellent comment. I was a bit too quick on that, and that kind of goes back to the earlier comment. So if you compare just means across games, you would not address what you are just referencing to, because this is actually an important aspect to not all penalties are equal in nature, in the sense that some of these penalties reflect the situation within the game. And this can change during the game, this can change across games. And probably, or most likely, or for sure, a series of 170 games might be selected as compared to all the 6,000 other games. So what we do here is, in the control variables, we have binary indicators for the score difference, and this goes up, as far as I remember, to each point from the perspective of the team in possession, up to 28 points score difference, plus and minus. So this is very, very granular. Larger and smaller than 28 points we have been together, but everything else is controlled by this score difference actually observed before the game. Before the play, sorry.
Before the play. Okay, got it. And then a really quick question. I know it may sound like splitting hairs, but speaking of also, different observations not being equal, not all, 250-pound players, for instance, are the same. Like it can be an athletic tight end who weighs roughly about the same as a lineman. So there's a different, body mass distribution in terms of fat and muscle proportions. So I was wondering, because I know you already mentioned that you have no way to control for the position, but I think it could be, like, down the line in your future research, a very valuable addition. Yeah,
I mean, that's an excellent point about the BMI story. That BMI can be driven up by how tall you are. It can be driven up by how much a percentage of your body is actually muscle as compared to fat. So in the end, what we do here in this slide, in this approach, is an attempt to do exactly this by telling that we look at these various weight categories, and it starts at 260. This is like compared to the normal population, that's quite high up there anyway. And probably most tight ends would be like in between, I would say, 240 up to 280 probably. So this would be the lower part of this approach here, and the upper part would be all the offensive linemen and the defensive linemen, basically. And what we do here is we actually compare on the right side, put simple, the defensive lineman who weighs 320 pounds and is only 6'1". And on the left side, we have the 320-pound lineman who is 6'7", who is much, much taller. And you would expect that the guys on the right side are those that are really obese, in the sense how the body mass index would explain it. So that should be addressing what you say here in your comment a little bit, not going really into the position stuff. And the other thing would be here this adjusted body mass index, because the adjusted body mass index pretty much tells us that it doesn't really matter how tall you are and how much body fat as compared to muscle you have. This body mass index should always be indicative whether you are obese and whether you have a health risk in terms of how your body physical characteristics look. And this is our best attempt to address this. We could do something with the position, but to be honest, with the position, it's always a difficult thing, because you have some categorization in there, but it's not really indicative what role you really play then. And it's kind of, but we could do that, yeah.
Wonderful. Thank you very much.
Thanks for your comments. Thanks.
Okay, thanks, Georgi. Any more questions and comments? Alex.
Hi. Thank you for a very nice and very interesting. Now, I have several comments. One of them is that there is well, you refer to this 85 degrees, which is you took it from a JPE paper, right? But there are some other studies that show that the distance from 14 degrees Celsius is actually the measure of how hot is it, or how not comfortable is it. Distance from 14 degrees squared, right? That's the measure. So
okay,
you could have tried this one instead of the linear one. So you have in the first, if you go back, you have in the first estimation. Yeah, you have so the first one you could have tried this one as well. So because linear is not clear whether this is really working. Just a technical point.
Yeah, I did not know that, but yeah, we have this non-linear approach here, which should kind of address this a little bit. It was surprising to us that we do not find anything in the lower parts of the distribution. Might be worth to look at this in more detail. But whatever we do in terms of categorization, the effect starts up here. So
no, I don't doubt the result.
But the 14 is nice. Yeah, we should try that. Yeah.
So the other one is, which are the cities that probably, because I'm afraid you have selection of the cities into this extremely hot temperature, and then we can have maybe you have only Miami, and then you have okay.
I don't have the heat map, so to say, with me in these slides, but if you look into the data, then you have treatments mostly coming from this area, but these two stadiums are domes. This one is a dome as well. These three stadiums are outdoor stadiums. We have an outdoor stadium in Washington, D.C., which should be treated several times. There is Soldier Field in Chicago, which should be treated several times. Probably.
So this would be just helpful for the reader to see what's going on, because this may indicate that actually you have kind of selection. You don't really check all the things, but you basically check only like several places, and then it may be because I don't like to play against Miami, or because I'm Miami, and then Miami maybe is a stronger team. Whatever, it doesn't matter.
No, that's an excellent comment. I should have prepared something like that. The other thing is that we approach this with our home team season fixed effect, so it's always variation within home team season. So that should help
this
us.
is how you control for ability of the team. Plus, you add the win percentage. By the way, the win percentage is up to the certain game, right?
Exactly, yeah.
And how do you deal with the first game of the season?
Zeros. But it doesn't matter how we construct it. It doesn't change anything. But at this point, it's zeros.
Okay. Thank you.
Thanks for your. I didn't know that with the 14. That's brilliant.
Thanks, Alex. We still have a little bit of time for any more questions and comments people may have. Looks like that might be your quota of comments and questions, Mario. So thank you very much for a really interesting talk. I learned a lot about American football in the process, especially the geographic locations was quite interesting. But really, really interesting talk, very thorough analysis on the effect of heat on actions, mental mistakes. We are going to return again next week with Linqing Jiang from the University of Essex, presenting fair play or winning ugly risk-taking behavior in elite competition under different rules. So thanks again, everyone. Thank you, Mauro, for a great presentation. Good to see lots of folk, and look forward to seeing you all again next week.